Hello and welcome to the Ali NOAA Climate Change Short Course. I'm David Herring, Director of Communications and Education within NOAA's Climate Program Office. And on behalf of our partners in the Oceanic Lifelong Learning Institute at George Mason University, it's a pleasure to bring you this lineup of world-class experts on climate science today. Today we're going to hear about what's the difference between weather and climate. To present that is Dr. Wayne Higgins, who's the director of the Climate Prediction Center based in Camp Springs, Maryland, which delivers predictions, monitoring, and assessments of future climate conditions on timescales from weeks to years to the nation and the world. And so today, Dr. Higgins is going to tell us about what's the difference between weather and climate, and how are climate scientists able to project future climate conditions when TV meteorologists sometimes struggle to predict weather 2 weeks in advance. So with that, please join me in welcoming Dr. Wayne Higgins.
What people really understand is the weather. You wake up each morning, you look outside, you make decisions about how you're going to dress that day. If there's a heavy rain or snow event, you act accordingly. But what you may not realize is that is part of a longer-term pattern related to climate, both variability and change. And so what I'd like to do is show you how weather and climate are linked as well. So the way we'll structure this presentation is as follows. I'll spend a few minutes discussing with you the distinctions between weather and climate, and then we'll delve into how they are linked. I think it's also important to recognize that, climate change, you hear that term over and over again, but there's more to climate than climate change. There's also climate variability, and I want to draw a strong distinction between the two. And again, I'll show you how they're linked, but I want to make sure that you understand the climate variability issue can be viewed as a very important one for forecasting as well as for understanding, how climate change is actually behaving. And then we'll have a discussion near the end of the lecture on long-term trends in weather and climate extremes. So I'll show you where we are in our understanding of, for example, how temperature and precipitation events, snowstorms, hurricanes, tornadoes, how they're changing and how that may in fact be related to climate change. I do want to acknowledge a large number of my colleagues in the National Weather Service, as well as in the NOAA Climate Program Office, including David Herring, who's been instrumental really in pulling this lecture together, that I'm very thankful for that. So let's now go into the first portion of the lecture on weather versus climate. And to do that, I'm going to tell you a little story about a young friend of mine. His name is Charlie. Charlie is a Minneapolis, Minnesota resident. This is 1971 when he was a little boy. And this happens to be the 4th of July. It's one of Charlie's favorite days of the year because he was together with all his cousins and family and friends. And many of the folks in his family were gardeners and farmers, and they used to love to talk about the weather. And they would reminisce about previous 4th of July events and other days in the summertime, and what occurred, whether it was stormy or nice weather. And sometimes there would be disagreements amongst members of the family. They didn't quite recollect things the same way, and this bothered Charlie. Charlie is a practical little kid, so he decided there was something he could do about this to solve the problem. Because he knew that in the local newspaper, they always reported the daily maximum and the daily minimum temperatures as well as whether it rained that day. So he decided, if I keep a weather log, then when these disagreements come up in my family, I can go to my weather log and point out to them, look, no, this is what actually happened, and solve the problem. So this is Charlie's solution. So, being an eager kid, the very next day he started going to the newspaper and started keeping track of things and recorded the weather in his log. It got stormy for a couple days. He thought that was great. But then the weather cleared up and got nice. And of course, kids have many interests. Charlie started to get a little bit lazy and bored with the process. And before you know it, the newspapers started to pile up. He stopped doing his log, and so his mom pitched all the papers. Well, the next year came for the 4th of July picnic on 1972, and all his family was there again, and they remembered that Charlie had said that he wanted to keep this weather log, so they were asking him about it, and of course, somewhat embarrassingly, he had to say, well, I stopped keeping my log, and they gave him some ribbing for that, and he didn't like it. So he thought about it, and he decided, well, since I'm going to be with these people every year on July 4th, maybe what I'll do is I'll at least keep track of the weather each July 4th. So I'll develop a good understanding of the weather for July 4th, so when they ask me, at least I'll be able to say, well, this is what occurred last year or 5 years ago or 10 years ago. So that's his plan. He's going to keep a weather log for July 4th. All right, so in between the food and the fun and festivities and fireworks, Charlie always kept track of the weather on July 4th. And so the years went by, and even though Charlie started to develop new interests, this is 1980, 10 years later, 4th of July again, Minneapolis, Minnesota, he still kept track of the weather in his weather log. And 10 years later, 1990, at the annual 4th of July picnic, now he's got a family, he's a young child. His parents aren't getting any younger in this picture, but still, Charlie's keeping track of the weather. 20 years now. Skip forward another 10 years, and here's Charlie with now 2 sons at the annual 4th of July picnic, and it's 30 years now that he's been keeping track of the weather. And so he decides that this is a good point to sort of stop and celebrate his log a little bit. And so he pulls it out. And here's Charlie's weather log for Minneapolis, Minnesota. And you can see the year, max temperatures for each year. And he looks at the data a little bit, and he realizes some years are quite cold, some years are quite warm, but those are really outliers. That doesn't really represent the way 4th of July normally is in Minnesota, in Minneapolis in particular. So he realizes, being again now a smart older man, that he can average the minima and he can average the maxima to get an idea of the climate normals for Minneapolis on July 4th. And so those are in fact shown at the bottom of the slide here. The average minimum temperature is 64. The average maximum is 84. So you can see there are some years, such as the ones I had circled, which are strong outliers. So the weather on those years was very variable compared to the climate normals, the maxima and the minima in this case. Now, by this point, maybe Charlie is a scientist. So he realizes maybe I should plot those normals on a graph. Scientists love to do that kind of stuff. So here are the climate normals for that particular day, July 4th, 30 years. That happens to, by the way, be a standard that's used by the World Meteorological Organization, 30 years as a climate normal. And so this is the 71 to 2000 period for July 4th at Minneapolis, Minnesota. Charlie realizes that those normals actually can be computed for every day of the year, okay? And so he goes to his local National Weather Service office, because National Weather Service offices keep climate normals, and so he plots those for the first 10 days in July. And Charlie is a very ambitious man, so he realizes he can do this for the whole year. And so here then are the climate normals for Minneapolis, Minnesota for the period 1971 to 2000, with the average high and the average low shown for the entire year. So we can expand on this concept now a little bit by recognizing that the climate normals, which are shown by the green bar there with the max being at the top and the min being at the bottom, are the climate. And what we're showing here on top of that is the weather for 2010. So each of those little blue bars is a day. And so you can see that there are some periods, for example, there's the period here in the spring of 2010 when many of the days had maxima that were much greater than the normals during that period. In fact, some of those days actually had minima which were greater than the normal maximum temperature for that day. So the weather in 2010 in that period was highly variable, and in fact you can see that the weather in general is highly variable, whereas the climate is fairly smooth. Also, it's important to recognize that we've looked at the normals for Minneapolis, Minnesota, but there are normals everywhere, okay, all around the globe. And so, in fact, you have to recognize that this is a specific set of climate normals and a specific weather situation for a particular location. So let's talk a little bit about, see what we've learned so far, by deciding whether the following phrases describe climate or weather. And I've just got a few of them here, but you could certainly do this yourself. What tells you what kind of clothes to wear? Weather. So what tells you what kind of clothes to buy? Climate. Okay, pretty easy, right? Can change dramatically from year to year. Weather. The picture that comes to your mind when you think of a faraway place. Climate. Just a couple simple examples there. So here now is sort of a synthesis of the information about weather versus climate. Weather is really defined as the state of the atmosphere at a given time and place. All right, and that state is complicated. It's actually with respect to many different variables. We talked about temperature just now, but of course we're all used to hearing about precipitation, moisture, wind speed and direction, pressure. So all of these variables can be used to help us describe the weather. Climate is actually what we call the expected frequency, or as I introduced the concept, it's the normal. But it's for these specific states of the atmosphere, such as temperature, moisture, wind speed and direction, and pressure. Even more, it's not just the atmosphere, but it's also the ocean, it's also the land surface, and in fact you could also argue it's the cryosphere, the ice component, with respect to all of these variables. So climate then encompasses weather over longer periods of time. So if you remember nothing else, I think it's important to remember that climate is a conceptual average, if you will, over longer periods of time of the weather. So then that naturally links to the next point, which is, okay, what's the distinction between a weather forecast and a climate forecast? Well, weather forecasts, as we might imagine, are event, location, and time specific. We talked about Minneapolis and the daily weather there. This is a fancy way, deterministic, is a fancy way of saying that it quantifies for you how warm, how cold, how much rain, how much snowfall. But weather forecasts are also probabilistic because we routinely will see, 50% chance of rain today. So both deterministic and probabilistic information make up weather forecasts. Climate forecasts, on the other hand, are averages of weather for usually a week, month, or longer, sometimes seasons, years, and in the case of climate projections, even decades or centuries. And they're almost always probabilistic, meaning that it is the average likelihood of warmer or cooler, or wetter or drier than average conditions. So that's a major distinction between weather and climate forecasts. So now let's move ahead to talk a little bit about how weather and climate are linked. Weather, climate variability, and climate change are inextricably linked. You can't really talk about one without some understanding of the other. And so, for example, one of the manifestations of climate change is actually variations in the numbers and in the intensity of weather events, including extremes. Everybody likes to think, I think, that with climate change we're going to expect more extremes in the future. But in fact, as I'm going to show you, there are places and times, seasons, in which at particular locations you actually will get fewer extremes. So it's very important for us to understand this linkage. Another manifestation of climate change is changes in the number and intensity of short-term climate events, which we can call climate variability. And I understand last week you talked about El Nino and La Nina. That's a great example of a tropical phenomenon, which actually occurs on what we call interannual or year-to-year timescales. It turns out that El Nino and La Nina also strongly influence the weather patterns, and I'll show you that momentarily. So not only is there a linkage between climate change and variations in the frequency and intensity of El Nino and La Nina, but in turn, there is a relationship between climate variability, El Nino and La Nina, and changes in the frequency and intensity of the weather events. So you can't really separate one without some understanding of the other. In the extratropics, there are also many types of climate variability. I think people are most familiar with the jet streams or the jet patterns. Well, those actually, as it turns out, also help us organize these storm tracks or the patterns of storminess. So you can actually think about individual storms as being organized into sets of storms. And so you begin to build up a sort of a climate variability made up of the individual storms. So let's talk just a moment about El Nino and La Nina again, sort of a review. El Nino then is characterized by a warming of the tropical Pacific, whereas La Nina is by a cooling that is relative to normal, by the way. And as a consequence of this periodic warming for El Nino or cooling for La Nina, you actually get a response in the atmosphere. Now this is just a fancy way here, organized tropical convection, of saying that you change the patterns of precipitation in the tropics. When you have El Nino, basically the warm water will support this deep tropical cloudiness and enhance the rainfall further to the east in the Pacific. Whereas in the case of La Nina, the pattern of deep tropical convection, moisture, precipitation is further to the west. So consequently then, there's an impact on the jet streams. So when you have an El Nino, the jet stream tends to extend further to the east, it's stronger, and it's actually suppressed somewhat to the south, carrying the storms into the southern portions of the United States. This happens to be in wintertime. La Nina, on the other hand, with that retraction of the precipitation pattern to the West Pacific, tends to cause the jet stream to be more variable, weaker in the south, and actually to go more up and over to bring storms down into the center of the country. So we tend to have in that pattern wetter Pacific Northwest, and actually an area here in the Ohio Valley that tends to be wetter, but drier and warmer than normal conditions along the southern tier. So the point here is, again, this pattern of climate variability, El Nino or La Nina, has a fundamental influence on the jet streams, and that in turn changes the areas that are warmer or drier or cooler or wetter than normal over the U.S., and hence the patterns of storminess. So to kind of reinforce this, I picked two of the major events from the last 100 years. The 97-98 El Nino was arguably the strongest El Nino in the last century. The 98-99 La Nina was also one of the strongest La Nina events. And what I'm showing here simply are the changes in the storminess, in fact the locations for major storms, and areas here that are shaded in yellow or red are those that experience the largest increases. And so you can see during El Nino we had lots of storminess along the west coast. We also had a storm track that was suppressed along the Gulf Coast, with even tornado outbreaks in the wintertime over northern Florida along the Gulf Coast, and strong nor'easters in the mid-Atlantic region. And some of you may remember the massive ice storm that we had in 1998 that caused almost $1 billion in damage to that part of the country. La Nina, on the other hand, the storm track tends to be located further to the northwest. Actually, typically it's west of the Appalachians. And in the Pacific Northwest is where we tend to get the hurricane storm force winds and the very heavy patterns of precipitation, but relatively dry in Southern California. So you can see how El Nino and La Nina, in this case these are two very strong events, really changed the pattern of storminess over the U.S. Well, it turns out El Nino and La Nina have many family members in these patterns of what we call natural climate variability. And it's important to understand that they can simultaneously influence the weather. So this is what makes it a challenge for weather forecasters and climate forecasters. We have to take into account all these patterns when we begin to put our forecasts together. So some of these patterns, as we've been discussing, originate in the tropics, and I'm actually going to show you one more of them, the ManJulian Oscillation, which is actually in honor of two very important scientists in the climate community, Roland Madden and Alex Julian. And both of these guys recognize that this phenomenon, the tropical Pacific, actually causes impacts very much like El Nino and La Nina, but on much quicker time scales. We'll talk about that in a moment. There are others that originate in the extratropics, and the two that I really want you to know about are the North Atlantic Oscillation and the Arctic Oscillation, because going back to the introductory comments that Alan made, you know, the last two winters we've had this parade of snowstorms in the eastern half of the U.S. That have caused all kinds of havoc. And it's interesting to point out that 2 years ago we actually had a strong El Nino in place, and yet we had this persistent negative phase of the North Atlantic Oscillation and Arctic Oscillation, which actually caused those snowstorms. So these patterns beat El Nino. And this last winter, we actually went into the winter with a moderate to borderline strong La Nina, and had, again, a persistent negative phase of the North Atlantic Oscillation, and as a consequence, had the parade of storms. So here again, the NAO beat La Nina in this case. So this is a very, these are winter wildcards, if you will, that we have to deal with when we are putting our weekly, monthly, and seasonal forecasts together. So let me just show you a couple more examples of climate variability. Again, I mentioned the ManJulian Oscillation. Again, this is a tropical disturbance, but unlike El Nino and La Nina, it has a shorter time period. It's on the order of 30 to 60 days, rather than from 1 year to the next. It does produce these El Nino or La Nina-like effects. In fact, very often you'll get an event that we call the Pineapple Express event here in the Hawaiian Islands. So the idea is that the moisture plume that comes up out of the Pacific towards North America crosses the general location of the Hawaiian Islands on its way to the west coast of North America, where we frequently will get very heavy rain events and periodic flooding. But it's not just the winter time when the ManJulian Oscillation can influence our weather. It actually also modulates hurricane activity. So let me show you that. But first, let me show you what goes on in the wintertime. So this is just a schematic, if you will, of sort of the typical evolution that we see with a ManJulian Oscillation leading to a heavy west coast precipitation event. So you'll start out with this disturbance of the tropics, and your jet stream sort of displaying kind of a variable pattern. But as time goes on, as we approach the extreme rain event, which is actually located here, what happens is this pattern of tropical rainfall shifts to the east, and your moisture plume begins to get caught up in the strengthening jet stream here in mid-latitudes. And as time goes on, that jet then continues to strengthen and extend towards the west coast of North America, drawing up in this moisture plume associated with this tropical disturbance, producing the very heavy rain event along the west coast. So it's an evolution that we can try to catch in our climate models to make a forecast out a week or two of these rain events and provide the type of early warning you need. But this is a typical scenario that we see. In the summertime, we very often find that the ManJulian Oscillation will modulate the tropical cyclone activity. And so here I've actually shown the tropical cyclone activity that you get when you have the enhanced or wet phase of the ManJulian Oscillation in the tropics. And so you can see there's all kinds of tropical cyclone activity. This happens to be an average over a 30-year period. On the other hand, the suppressed or dry phase of the ManJulian Oscillation produces very few tropical cyclones. So this then is a very useful way of giving us a heads up on whether we can expect tropical cyclones in the Gulf or not during an active MJO event. Now I should point out also that I'm just showing you here the Gulf Coast, and in fact the MJO modulates the tropical cyclone activity in all of the basins right around the global tropics. So this is useful not just for landfalling tropical cyclones here in the U.S., but actually also in Asia and elsewhere. So I mentioned already the Arctic Oscillation and North Atlantic Oscillation, so let me just reinforce that the last 2 winters, we've actually had the persistent negative phase of this Arctic Oscillation. The distinction between North Atlantic Oscillation and Arctic Oscillation is really relatively minor. The North Atlantic Oscillation is really just the projection of the Arctic Oscillation into the North Atlantic. But if you were to correlate these 2 patterns of climate variability, they correlate very highly, above 0.9. So each pattern really produces, in the case of the negative phase, a weaker than normal polar vortex. When you do that, actually you end up getting a relatively warm polar region and a relatively cold mid-latitudes. With this relatively cold mid-latitudes, you have more cold air outbreaks, more storminess, more snowstorms. And that's the kind of thing we've seen each of the last 2 winters. And so the challenge has been that this has been a very persistent thing. Both winters we had this persistent negative phase of the Arctic Oscillation, NAO, yet we currently have no capability to forecast the phase of the Arctic Oscillation or that North Atlantic Oscillation beyond a week or 2. So that's why I said earlier these are winter wildcards. We have good skill in being able to forecast an El Nino or a La Nina out to 6 months. We have very little skill in being able to forecast the Arctic Oscillation or the North Atlantic Oscillation out a week or 2. So if these guys hang around all winter in a persistent negative phase, it wreaks havoc on a seasonal forecast. So again, the Arctic Oscillation produces significant impacts, and I'm showing here both the warm side as well as the cold side, so the positive phase and the negative phase. And again, this is the pattern that's predominated each of the last 2 winters. So I'd like to move ahead now to talk about the distinction between climate variability and climate change. I hope at this point you have a better feeling for what we mean by climate variability. We mean the relatively shorter time-scale climate patterns, meaning El Nino, La Nina, ManJulian Oscillation in the tropics, or the North Atlantic Oscillation, Arctic Oscillation in the extratropics, as opposed to climate change, which is really referring to the longer time scales beyond, say, year-to-year variability. So let me reinforce that point here, that climate change is really the departure from the expected average. We talked about normals already, weather or climate normals for a given place and time. So what I mean here is that in contrast with extreme events like, getting a snowstorm in Florida, what we are talking about with climate change is the long-term shift in the average weather. So I want to talk about different types of climate change, and we'll talk first about abrupt climate change. But before we do that, let me emphasize why it's important. It's important, clearly, because if we have, for example, global temperature increases, this in turn is going to have significant impacts on a wide range of human issues, like human health, our economic activities, our national security. 40% of us in the U.S. live within 10 miles of the coast. Many of our military installations, our nuclear power plants are located near the coast or on the coast. So if temperature warms and Arctic sea ice is melting to raise sea level, obviously you have coastal inundation issues which are going to influence planning decisions for infrastructure, where people choose to live, and so on. So clearly, we worry about climate change because of the significant human impacts that have come along with it. So to be prepared for the effects of these potential impacts, we need to know how much the Earth is warming. We need to know for how long it's been warming and where it's warming. So as I'm going to show you, even though we talk about global warming as sort of this global temperature increase, there are areas of the globe that, depending on the season, are actually cooling in the last 50 years. Answers to these questions obviously are going to provide a better decision-making basis for us in preparing. In the Weather Service, by the way, we do preparedness and early warning. In the Climate Services arena, we do longer-term planning for adaptation and, of course, also mitigation. And so really what we're saying is that we have to understand climate change to be prepared for its effects. So I mentioned we talk about abrupt climate change. Abrupt climate change is a shift that occurs relatively quickly. Typically it's a decade or less. But as the shift occurs, it tends then to persist for decades and sometimes millennia or even longer. We've got three sort of characteristic examples of abrupt change. Rapid change in glaciers, ice sheets, and sea level. It's a good set. Changes to the hydrologic cycle, such as desertification, which of course is related to increases in drought. And rapid releases of gases to the atmosphere, such as atmospheric methane. So let's look at a few more examples of abrupt change. This happens to be a look at the glaciers in Glacier National Park. This is the Shepherd Glacier in 1913 as compared to 2005. Quite a difference. And in fact, the latest projections that I've seen are that by 2030 there'll be no more glacier ice at that location. This happens to be the water supply for Lima, Peru. Lima's water supply is clearly diminishing. This is 1978 versus 2004. And I'd like to point out that there are over 1 billion people around the globe that depend on glacier melt for water supply. So clearly this is an important issue. This is somewhat startling, I think. Plant hardiness zones. This is the 1990 map, and you can pick your favorite location. And you can compare it to 2006. I haven't seen the update, so I apologize for that. But virtually all locations, what you'll find is the zones have shifted northward by up to 200 miles. So, for example, in much of this area, whereas we were a 6, now we're a 7. So basically the plant types, the flora are shifting north and almost pretty uniformly across the U.S. Arctic sea ice, I mentioned that earlier. This happens to be just a quick look. I think these are based on averages in the month of January from 2001 through 2006, showing from satellite perspective that clearly the sea ice is diminishing, and I can tell you through to the present day that that diminishing trend has continued. I mentioned desertification. This happens to be the Aral Sea. This is 1973. 1987 and 2000, and fully 60% of the Aral Sea has disappeared and has been replaced by really a very dry and dusty plain in this region. So clearly that has major implications for planning, infrastructure. So as opposed to abrupt climate change and climate change itself, what is global warming then? Well, global warming really refers to the fact that the atmosphere near the Earth's surface is warming. But it doesn't tell you anything about implications for the cause or magnitude of the warming. So I want to amplify that a little bit. So keep in mind that global warming is really one of the many types of climate change. And in fact, the Earth has experienced global warming in the past, and it will continue to experience it in the future. And you know, what's important here is the magnitude of the warming, and as well as the trend. So this also implies that an overall average warming is occurring across the entire globe. And as I mentioned earlier, when we look at particular regions and seasons, we actually see that at the present time, they are not experiencing warming. So let's look at that a little bit more. So here is a picture of the annual trend in temperatures from 1901 to 2005. It does show that the global surface temperatures have increased for the global average of 0.75 degrees since the late 19th century. The trend is currently 0.13 degrees C, and that's based on the past 50 years of data. But as you can see, the warming has not been uniform. For example, I'll draw your attention to the southeastern United States, where actually there has been a modest cooling in this period. There are other areas, for example, in the North Atlantic. But on the whole, the recent warmth has been greatest over the far northern portions of North America and over Eurasia. And those areas, of course, in size are greater than the areas where the decreases have occurred, as we see also the warming has occurred over the ocean areas. So in the net, we do have this upward trend. Another way to look at this is to look at a time series. And so you may have seen this already in an earlier class, but if you haven't, I'd like to reinforce the fact that whether we look at year to year or we look at it by decades, clearly in the past 5 decades there is a rapid increase in the global temperature anomalies. And I find it interesting, if you look at each of the last several decades, for example, let's pick the last 10 years here, that each of these years is warmer than the mean of the previous decade. So, and that actually works for the past several decades. So it really points out how quickly the temperature trend has been increasing. So how do we know the Earth's climate is warming? You could pick many different parameters to talk about this, but if you think of this as basically being land and ocean temperature observations from weather stations and ships and buoys and satellites, what we do is we combine these together in a judicious way that takes into account where they're located, what their quality is, and we put them into what we call a time series, and I just showed you a time series in the last slide. And we use that for whatever parameter we're interested in to see whether or not we have an upward trend or a downward trend. So if we talk about ocean heat content or sea level or sea surface temperature or humidity or air temperature, we've seen upward trends in all of those parameters. If we talk about glacier ice or snow cover or sea ice, we've seen downward trends in those. That's the way that we know that the Earth is warming. So I get this question all the time, are El Niños related to global warming? And the answer really is that El Niños are not caused by global warming. In fact, we've had El Niños, we can look back even up to millions of years in the prehistoric records we have in paleoclimate and see evidence of El Niños. But what is well known is that this warming that we see with El Niños, periodic warming in the tropical Pacific, is obviously controlling the strength of the El Nino. And so the jury is really still out on whether, if we continue with this warming trend, whether we can expect there to be more El Nino events than La Nina events in the future. There's not an answer to that question that I can give you, except to say that it's a subject of ongoing research today. So an important aspect of global warming that you need to understand is the greenhouse effect, because we have our built-in global warming, if you will, that occurs naturally. The natural greenhouse effect basically proceeds by heat absorption by atmospheric gases such as CO2, also water vapor, and other trace gases. And in fact, it warms the Earth by roughly 70 degrees Fahrenheit more than the Earth would be without the presence of these gases. So in that sense, the gases help the climate system to act like a greenhouse. The enhanced greenhouse effect, though, is simply the recognition that human activities have increased greenhouse gases, and I'll show you a lot of evidence of that in the next several slides. And this then artificially increases the Earth's temperature by another 1.4 degrees Fahrenheit on top of the natural warming that we experience from the greenhouse effect. So in other words, the concern is, do human activities, which are linked to increases in greenhouse gases, which then in turn are linked to this increase in global temperatures, continue to accelerate this natural greenhouse effect? So our greenhouse gas is increasing. Well, I think it's pretty clear they are very rapidly. This is the carbon dioxide time series, and this actually shows a period since the year 1000 right through to the present. And certainly since the period of the Industrial Revolution, starting in about 1680 or so, we've increased from about 280 parts per million up to present-day levels that are about 380 parts per million, with the current increasing trend on the order of about 1.9 parts per million per year. I might add that if you go back 650,000 years, you will find that the levels that we are at are unprecedented. So there clearly is evidence that since the beginning of the Industrial Revolution, and with the fact that we currently have 6 billion people on the planet, and we never in the historical record have had 6 billion people on the planet, I think you can't get away from arguing that these increases are related to human activities. And so clearly we know where these gases come from. It's from industrialization, it's from the agricultural practices we use, it's certainly from the automobile, it's from the way we heat and cool our homes. Who's doing the emitting? Well, clearly from this diagram, it's the industrialized nations. The U.S. actually leads the way per capita in this area. There are up-and-coming issues, of course, with the areas whose populations are growing the most rapidly, such as China, and actually more recently also India. So how do we know that humans are the primary cause of the warming? And this is where we're going to now get into a discussion about modeling. Okay? But first let me point out again that there are both natural and human factors that can lead to climate change. We talked earlier about some of the natural variability. Let me emphasize that even if we were not to burn any fossil fuels, we would still see this natural variability in the Earth's climate. Solar cycles, I haven't talked about those, but those proceed on sort of an 11-year cycle, can influence climate. Volcanoes, we have a periodic volcanic eruption that can actually cool the climate for a year or two. We've seen that in the historical record a number of times. So the point is, from models, and I'll tell you more about what I mean by models in just a few moments, from model evidence we know that the observed warming over the last half-century is primarily due to human factors. Why do I say that? Here's a look at the observed temperatures over the last almost 100-year period for the globe. And you can see that it does show this trend, upward trend in temperatures. And then what I'm showing is also, if we take a model and we try to reproduce that observed temperature time series over this period, but only use the natural forces, so the solar cycles and the volcanic eruptions and so on, you see that we are unable to capture the observed temperature trend. On the other hand, if we then introduce also the human forcing, and by that I mean the emissions of greenhouse gases and so on, that what you are able to do with both the natural and human forcing is reproduce the observed temperature trend. So this is clear evidence, at least for the period through to almost the present day, that the natural and human forces are both necessary to describe what has occurred. So what can we expect in the future? That's the $64 million question. Obviously, we can do scenarios using climate models where we can ramp up the greenhouse gases from maybe a little bit to a lot, and we can see what is the range of uncertainty in those projections of climate in the future. So we change certain parameters, CO2 is a favorite one, and we look at trying to understand how the climate would change in response. And so this gets to a very important point, which is credibility. To credibly project a parameter, so projections, by that term I mean really going out well into the future, decades to centuries, we must have a climate model that can credibly treat the past. So going back to the previous slide, I hope I've convinced you that we have climate models that are capable of credibly treating the past if we use both the natural and the human forces. All right, so another important point, what people really care about are the extremes. When you wake up in the morning, if you're having a snowstorm, that's what impacts your life. So we have to have climate models that can do the weather statistics also. In other words, tell us, are the frequencies or numbers and are the intensities of the extremes going to increase in a future climate scenario? So that means that the model has to capture those statistics properly. So I wanted to say a little bit more about what a climate model is, and I think that to boil it down to its simplest level, you can think of it as being kind of a virtual reality, like the virtual reality of a video game. But what we do is we take the math and physics that describe the atmosphere. This is actually the equations of atmospheric motion. And we use them to build what we can think of as a virtual Earth. We code these equations up, and we then, on a computer, take the initial data from around the globe. It could be in the case of a weather forecast, atmospheric soundings, as well as today's temperatures and precipitation. And we use that information together with this model on a grid, and then we put that on a supercomputer, and we integrate it forward in time for a few days to produce a forecast. In the case of climate, we may use the ocean conditions, which actually are relatively more slowly varying. We may use something about the land surface conditions. Is the soil moisture for the season running above normal or below normal? Again, same idea. We put this together with the computer model on a supercomputer, and now we may integrate forward in time for months or seasons or even a year or even decades to produce a climate prediction or a projection. So again, think of it as kind of like the virtual reality, but in a virtual Earth. And it's gotten to the point now where our virtual Earths behave an awful lot like the real one, at least in the short term, and as I'm going to argue, even in the longer term. And so that we can use these models to predict the future. So now we can ask ourselves, okay, how do we want to use these models? So I've listed here some parameters that we might want to think about. I've listed here the level of interest of making good forecasts of those parameters to decision makers. Okay, so that's the bottom line. If you're going to plan or prepare for climate change, you need to think more about the, how that is related to the decisions you need to make. And then, what is the current ability of our climate models to reproduce? So when we talk about the mean annual global surface temperature, which as it turns out, almost all climate models are capable of reproducing with almost exceptional ability. Turns out, for decision makers, there's no interest in that, okay? It really doesn't relate, because if you think about politicians, for example, they have a particular area that they have constituents who care about climate change, and so that's more regional or local. So, but the global temperature change doesn't really relate to the kinds of decisions they have to deal with. On the other hand, regional and seasonal mean temperature and precipitation is much more considerable interest. And it turns out that climate models do have some fair ability to get the surface temperature. Unfortunately, it turns out precipitation isn't so good. We can forecast precipitation for a few days or even maybe a week or two. There may be a little bit of skill. I have to say this as a seasonal forecaster, a little bit of skill in seasonal time frames. But when we start talking about decades or centuries, there's very little skill there. Now, when we get to where's the intense interest, it's on regional and seasonal risks of weather extremes, the high-impact billion-dollar events. And unfortunately, we have very little ability at this point to predict those. So this is sort of the state of the art. A long way to go. I view this as job security, because there's a lot to do. So, okay, so then, you'll ask me this question, all right, if we can't predict the weather a week out, well then why should we believe 100-year climate projections? Well, remember a few minutes ago I told you that we can at least test scenarios where we can take a climate model and we can put in, say, a little bit of CO2 increase, or we can put in a little more, or we can put in a lot. All right, and we can look at, in this case, I'm showing you a set of projections for, say, temperature out to the year 2100. And from this bottommost projection to this topmost projection, we get a range of uncertainties. All right, and what we hope is that as we improve our climate models, these ranges get smaller and smaller. So the hope is that as we understand the climate system better, as we improve these virtual Earths, we make our ability to project climate out 100 years more certain. All right, and so each 5-year period or so, we come out with a new set of assessment reports. I'm not going to talk about those in detail today. I believe you're going to actually be hearing about those assessments from Tony Genatos and other lectures later in the course. But one of the things we'll be very excited to see with the next assessment is to what extent the uncertainties which we had in the previous assessment have been reduced going forward. So let's now talk a little bit about trends in weather and climate extremes. And this actually is my favorite topic of all, because I get more questions in this area, I think, in my position than in any other. People really want to understand what they might expect in their lifetime and in their children's lifetimes as regards how, weather extremes are going to change in their backyard. And again, let me remind you that climate, both variability and change, are inextricably linked to this question. So we've already, I think, motivated the fact that weather and climate extremes have significant human impacts. To sort of address this point a little bit technically, perhaps, let's pretend that this is today's climate, and this is for temperature. Temperature tends to have a normal distribution. So over on this end of the distribution, this is our cold temperature extremes. We could pretend this is Washington, D.C. This is the average temperature, and this is hot temperature extremes. Well, in a warmer environment, say where the climate shifts towards warmer, this whole curve will shift to the right. And so in this new climate, it doesn't matter whether it's 10 years or 100 years from now for the purposes of this argument, obviously you're going to have less cold weather in the new climate than you used to, or what you're used to. You're going to have more hot weather in this new climate than what you were used to. And you're going to have a lot of record heat, because you're going to be experiencing events that you didn't experience in the previous climate. The same is true for precipitation. So if this is today's climate, and this is the number of light rain events that you get, and this is the number of heavy, and it doesn't really matter the specifics. But the point is, if you shift to a new climate where there are fewer or less light precipitation events, and there are more heavy precipitation events, then obviously that's going to influence the numbers of droughts that you get, the numbers of floods that you get, and so on. So one of the things that we like to do with our climate projections is look at how these profiles, we call them distributions, change as we move to different climates. As I mentioned before, obviously these are events in the extremes anyway that have significant impacts, and this is just to make the point that the billion-dollar weather disasters in the U.S. have been increasing, so clearly there's an economic reason for wanting to get a better handle on these extreme events. So I'd like to share with you some interesting results. They're actually from previous assessment reports. First I'll show you the observed changes, and then I'll show you some projections. Again, keeping in mind that the observed changes are pretty certain because we have good data. The projections are more uncertain, and particularly more uncertain for precipitation than temperature. So here are the observed temperature extremes. First of all, we have experienced more unusually warm days and nights in recent decades. There's evidence of this. I'm actually showing you the trend and the number of days with unusually warm daily low temperatures, because as it turns out, the daily lows are really what especially elderly folks are very, very susceptible to. Some of the worst heat waves in the U.S., for example, in the Chicago area, have caused a number of deaths because the daily lows stayed above 80 degrees Fahrenheit. It's not so much the daily highs, it's just this continued period of high heat and humidity. Well, it turns out that the upward trends in these daily low temperatures are particularly pronounced over the western half of North America. It also turns out that there is an increase in the number of heat waves in recent decades, but still the decade of the 1930s stands out as the most severe decade for heat waves in the past 100 years. This is just a global look at the same kind of thing. So this is temperature extremes, again, observed changes, cold nights here, cold days here, and this shows you the downward trend in cold nights, also the downward trend in cold days, though there are some exceptions. Remember I pointed out earlier the southeast U.S. has actually been cooling, and actually there have been slight increases in the number of cold days in the southeast. More unusually warm days and nights. Again, showing down here that warm nights, most of the globe, they've been increasing. Warm days as well, except in the southeast. Increasing numbers of heat waves, yes indeed, that has been occurring, but again, the 1930s stands out as being the most severe. So what about projections of changes? Again, warm days and nights and heat waves are very likely to be more frequent. Here I'm showing first of all, a simulation of the observed very warm nights over the period from 1900 to 2000, and then beyond that, a series of climate projections out to the year 2100, ranging from, and these are for various scenarios which are listed down at the bottom. Don't worry about the details. Just keep in mind that it's scenarios that range from basically small increases in CO2 to very large increases in CO2. And what you're seeing here are the envelopes of uncertainty for those different emission scenarios. So you can see there's quite a range here. This is the percentage increase in the likelihood of very warm nights. This is the top 10% in the distribution of very warm nights out at 2100. And so you can see it's pretty uncertain. So anywhere between, I guess that's about 10% and something greater than 90% increase for the suite of scenarios. So that really doesn't make me feel very comfortable about our confidence at 2100 in the increase. However, as you see, as we come back towards 2010, 2020, 2030, the confidence is much greater. I think a key point here is the increases have been proceeding rather expeditiously through the entire 100-year projection. Temperature extremes, I like to look at return periods. What do I mean by that? That's how often do we get an extreme event like one we just experienced. So this happens to be projection of extremes for hot days. This is the top 1% of the distribution. So in fact, it turns out it's days that have been currently experienced once every 20 years. So we asked how often those events would occur in the future. And as it turns out, by 2100, warm days that occurred in that top 1% of the distribution every 20 years would actually occur every other year over much of the western half of the U.S., and actually even up to every 3 years or so over the eastern U.S. So in other words, if the top 1% of the distribution means a 100-degree day in Washington, D.C. every 20 years, it would mean a 100-degree day every 3 years or so in the year 2100. Now, 100 degrees may be a little low. I know we've had some days in D.C. since I've lived here over 100 degrees, but I hope you see the point. The point is that these extreme events that we've experienced in the past are going to become much more frequent. Okay. So let's talk about precipitation. So these again are the observed changes, and this is for the intense precipitation events, the heaviest 1% of the distribution again. And you can see that whatever region you pick in the U.S., there have been increases. If you integrate this together, it's a 20% increase over the past century. And I might add that when you look at the total distribution of precipitation, you find that there's actually been a 7% increase for the U.S. as a whole. So whether you're looking at light rain events or intense rain events, when you add them all together, you actually still get a net increase. Turns out there have actually been some decreases in light rain events, and I'll show you that in a projection momentarily. This, first of all, is a projection that looks at the increases in precipitation intensity. Again, the same type of thing, where with the last 100 years, we're able to pretty credibly simulate what has occurred. When we do the projections, we're looking at the increases in heavy daily precipitation out to 2100. This is the top 5% of the distribution. And we find, in fact, the confidence intervals are very broad, somewhere between just greater than 0 and 100. So by 2100, the confidence is pretty low, I would say. On the other hand, in maybe the next 20 to 30 years, you can see that the confidence is reasonable that we're going to continue to see increases in heavy daily precip events for the U.S. I like to look at precipitation events this way. This actually looks at the projected changes in precipitation intensity by intensity level, ranging from the lightest events through to the heaviest events. And this again is the percent change. The bottom line is, as the emissions scenario increases from slight increases in CO2 by 2100 to large increases by 2100, we have increasingly large decreases in the lightest precip events and increasingly large increases in the heaviest precipitation events. So it's like we're getting a skew where we don't get light rain days and we get lots more heavy precipitation events. And again, when we talk about return periods, now events that are currently experienced every 20 years, and this happens to be again for the topmost portion of the distribution, they would occur every something like 4 to 6 years in the northeastern United States. It's interesting to point out that the largest increases over the last century have been actually here in the northeastern United States. And so, in fact, if you put that together with the fact that the return periods are also the shortest in the northeastern United States, doesn't paint a very pretty picture for extreme rain events. In other words, we can expect more flooding events in the future. Snow cover, very quickly now, there have been decreases in snow cover, but I would like to point out that this happens to be a plot from 1920, excuse me, with decreases starting in the 1960s for the March-April time frame. If I were actually to show you a similar time series for the earlier part of the winter or the autumn, we don't actually see significant downward trends. Tornadoes. Turns out that there's no trend in tornado occurrence that can't be explained by trends in reporting. This happens to be the number of strong to violent tornadoes. And when I first looked at this, it almost looked like there's a downward trend, but as it turns out, it's not significant. So we wouldn't want to claim that there's a downward trend in tornadoes. Hail. This happens to be the record large hailstone that fell in South Dakota last year. It turns out also there's no trend in hail that can't be explained by changes in observing and reporting, though we should recognize, of course, that people are moving into more hail-prone areas. So in fact, there have been larger increases in hail losses and therefore claims and insurance, for example, due to hail losses because folks are living in storm-prone areas. In fact, this was some damage to a golf course that was in response to the same event that produced this record large hailstorm. This question comes up all the time, and in fact, we're just now heading into the time of year when NOAA produces its annual hurricane seasonal outlook. People want to know, are hurricanes increasing in the Atlantic Basin? And so what I'm showing here is the annual numbers of hurricanes and major hurricanes. Major hurricanes are those that are category 3 to 5, as well as the decadal variations in hurricane activity over the same period. And the argument has been, well, if human activity is warming the globe, then that means we're warming the sea surface temperatures. If we warm the sea surface temperatures, that's the juice for hurricanes, if you will. And so one could make the argument that humans are having a discernible impact on Atlantic hurricane activity. It turns out also that the last roughly decade and a half, actually since the mid-1990s, has been a very active period in the Atlantic Basin where we've had more storms than in the previous several decades. But if you look at these time series, and whether you look at the decadal time series or you look at the individual years, I think you'll agree that the kind of activity that we've seen in this most recent decade and a half is not unprecedented. And I might also point out that since the advent of satellites, which was basically in the late 70s, we've been able to see more Atlantic hurricanes than we could prior to the 1970s. Unless a storm made landfall, we might not have even known of its existence out there in the middle of the Atlantic unless it was reported by a ship after it docked in port, and so on. So the point is that changes in our reporting methods and our ways of observing Atlantic hurricanes may in fact be confounding our ability to separate out and observe trend or increase. So the jury really is out on whether or not we are seeing an increase. There is considerable decadal variability in the Atlantic. So let me begin to close now by saying something about the big unknowns out there. Obviously, projections, climate projections, particularly of things like extremes, are very societally relevant. We need to capture the uncertainties in order for us to be able to describe where and when and how those impacts will occur. And so this is very much on the agenda of the climate community as one of the top factors that we need to address as we move ahead with climate models and trying to provide climate information to users for decision making. So reducing uncertainties in forecasts at specific locations. Weather, climate variability, and climate change are inextricably linked, and I think most people understand the weather pretty well. I hope that the information that I presented here this morning provides you a little bit of insight on the climate side, that climate variability also controls the weather. And El Nino and La Nina in the tropics, they're very relevant. ManJulian Oscillation in the tropics, also relevant. In the extratropics, the North Atlantic Oscillation, the Arctic Oscillation control the patterns of storminess. They explain why you can get snowstorms in Washington, D.C. in a parade in a global warming scenario. I think they help us also understand how important it is to improve our ability to understand how climate models are able to reproduce these. So recognizing that the climate system can respond in many ways and produce surprises like parades and snowstorms in a global warming scenario are important. I use the word nonlinear here because, again, some of these patterns of climate variability, like the North Atlantic Oscillation, are relatively unpredictable. And there are other things out there in the climate system that we don't even know the existence of, that we have yet no understanding or ability to capture in our climate models. So we have to recognize that there are climate surprises out there as well. So let me then finish up with just one slide summarizing the takeaway messages from this lecture. First of all, I hope you agree that climate change is manifested as changes in the number and intensity of weather events, including extremes. It doesn't just mean increases, it can also mean decreases in extremes, or even staying much the same. And clearly these have significant human impacts. There are very important long-term trends. Showed you examples for precipitation and temperature, and how they influence the climate of North America, and this is also true around the globe. We don't want to dwell too much on precipitation and temperature. NOAA, in the recent planning that it's been doing to organize climate services, recognizes the importance of other issues like sea level rise, and of course you have to put on top of that winds, waves, tides, and surges. And if you live along the coast, all of that is relevant to planning, infrastructure, where we live, and so on. Links between trends in greenhouse gas concentration and trends in some weather extremes are not fully established. I showed you, for example, that with hurricanes, the jury's still out really on the explanation for what's going on in the Atlantic Basin. There's tremendous decadal variations in hurricanes that we need to separate from these climate change influences. Climate models are very important tools for us, and we want to increase their credibility by improving our understanding of what's out there, what the climate phenomena are that are relevant, and also improving our ability to detect man's influence on climate. And I think that recent progress in our ability to predict phenomena at the interface between weather and climate has been really impressive in the past years, I would say a decade or more. I think it's really serving as an important way forward for Earth system science. I've spoken, I think, mostly on the atmospheric component. I know that in the lectures to come you're going to be hearing a lot more about CO2's influence on climate change. You may also be hearing more about the ocean's influence on climate change than I've spoken of. But I think that we have to take an integrated view. Obviously, it's an interdisciplinary activity, and we aren't growing necessarily out of our universities a cadre of experts who have interdisciplinary expertise. And actually, I think that's kind of a plug. That in our academic settings, I really think we need to be thinking more about climate change experts who also understand resource planning or infrastructure planning to make that linkage between what we begin to get out of our climate models and making decisions at the regional and local level. So I'm going to leave it there, and hope you have plenty of questions for me. These are some additional resources that I strongly encourage you to check out. If he hasn't already, I want to give a plug for the Climate Service Portal. Dave Herring is the lead on the Climate Service Portal, and it is a marvelous multi-audience tool that includes a lot of the information I've shown you here this morning and much more. It has a Climate Watch magazine. It has great information on data that's available from NOAA. It also has some articles on adaptation and mitigation and so on. The Climate Prediction Center, where I work, we have a lot of products that span, again, climate prediction, monitoring, and assessments. We have the IPCC website. I mentioned the assessment reports that are out there. There's great information at that website. U.S. Global Change Research Program also does there's a national assessment for the U.S. You can get there. The National Climatic Data Center, they are the archive for much of the data that's used for the national assessments and also for the IPCC. They're actually the source of much of the information on climate normals that we spoke about at the beginning of the lecture. And then there's a Global Change Master Directory, which also captures a lot of the climate change information that you might be interested in. So with that, I think I'll close. I'm not an expert on volcanism. I would venture to say, though, that it would be tenuous at best to make that connection. But I would argue that unless you had an expert on volcanism here to contradict what I say, that there really isn't a strong connection. Thank you. Many climate projections, they're initialized, okay, and then they let it go for 100 years without updating the forcing, okay? That's a particular type of projection. A way to address the issue of climate feedbacks is to periodically update the forcing. Now, in a projection, obviously you can't do that. But with a prediction, say you're trying to simulate the last 100 years, what you can do is you can start the simulation, and then you can periodically correct the conditions, that you initialize with, and then go forward. And you can turn things around and kind of change them away from where the climate may be heading to see what impact that has on the simulation. So there are methods that climate modelers use to look at that, and there's great care, actually, that's taken to make sure that we have a good understanding of, what those flips might mean. It's a combination of both natural and anthropogenic, and I don't know that we understand the exact balance, but as I tried to show, if you just take the natural component, you cannot reproduce the observed temperature trend over the last 50 years. It's until you include the CO2 warming and the other trace gases in your climate model simulations that you reproduce the observed temperature trends. So you need both, the natural and the anthropogenic. So if we stop driving Priuses and continue emitting vast amounts of CO2, I would argue, we're going to continue with the upward projection of temperatures, and our climate models need to have, that as part of the scenario to reproduce what we're seeing. So it's not just natural. In fact, the natural piece, is important, but you need both the natural and the anthropogenic. The jury's out on what would happen, if the interhaline circulation and the the global circulation in the oceans collapses. But I can tell you that from some of the decadal work that I've seen that it would have a profound influence on the basically the uncertainties increase greatly in terms of the numbers and types of extremes. I've seen model projections where they turn off the ocean circulation and then they compare it to projections where they leave it going, and the uncertainties go up greatly. But in the end, those uncertainties for extremes also go up greatly. So I can't really put a bounds on it, but I think it's a very, very important and profound question that needs to be addressed. First of all, I can understand why Chicago and Seattle are planning in that way. If you consider that the Arctic sea ice, which between the Arctic and Antarctic, we're talking about something like 90% of the fresh water in the world. If we're losing that sea ice, obviously the Great Lakes levels are rising, and so if you're the mayor of Chicago planning infrastructure, you want those climate model projections to become more and more certain. Same would be true in Seattle, where if we expect more, hurricane storm force winds, and influences on the sounds and so on. I think the sea level rise issue is vital. So now, what's the point about cadre of climate scientists? Well, in my role as the director of the Climate Prediction Center. We hire a lot of people, and so the folks we hire typically have very good expertise coming out of the universities, and I've hired a number out of the University of Maryland, so I can use that example of really understanding how climate models work, climate simulations, climate predictions, climate projections, even how the physical parameterizations are constructed, and how to interpret the output. What they don't have a good understanding about, though, is why the mayor of Chicago needs to be planning for the next century. Why Seattle needs to worry about sea level rise for infrastructure planning. And so what I was simply trying to say is that we have to connect the physical and the social side more effectively. And I think the only way that's going to work, we can try to train, and we are doing that. In NOAA, we're trying to train people to be more interdisciplinary in this sense, and we're doing a lot of outreach. Dave can certainly speak to that in the Climate Program Office, but we're also trying to develop intermediaries through regional integrated science assessments, where we have people in the region working with, say, the mayor of Chicago, on taking NOAA information and making it useful. But I think until we really educate the cadre of up-and-coming scientists, social and physical, to be more interdisciplinary, we're not going to be as effective as we need to be. Boy, that's not I would argue it's the second one and maybe a little bit of the third. I think that the data speaks for itself. Those are the facts. I think that very often politicians are answering to their constituents, and I think that we have a job. I'm certainly here today to, I think, begin to address part of that job. As a scientist, I want to make sure that we get the facts out to the public and let them make the decisions, and hopefully that'll feed back then on who's in office.